Okay, let's get started. Can everyone hear me?
Yeah.
Okay, awesome. Okay, so we're going to pick up where we left off. With this slide right here, we just finished talking about the relation between conjugate acid-base pairs of Ka and Kb. Anyone have any questions on it before I move forward? Okay. So we're going to start talking about finding out the strong acid and strong base and weak acid and weak base equilibria. In other words, equilibrium. So good news about this. If I'm looking at a strong acid or a strong base, I know that it dissociates completely. So it will completely separate into H plus and whatever else it might be, OH minus in the process. So if I look here, I have 0.1 molar HNO3. So my total amount of H plus is just 0.1. Does that make sense so far? Anyone have any questions? Okay. So 0.1 is just going to equal to 0.1 of my acid. This means that I can just go ahead and solve for my pH. I don't need to use an ice table here. I know the amount that I have. Okay. Any questions before we continue? All right. So with that said, when I deal with weak acid equilibria, this is when I do need to use my ice table. So for weak acid equilibria, the number one thing you want to pay attention to this, you want to make sure it is balanced. You can go ahead and assume that weak acid has a very low Ka. So we can go ahead and assume our 5% rule in most cases. The minus or plus X usually is removable. Okay. Does anyone else need more time with this before I move forward? So we treat this the same as we would a normal ice table with the thought that the 5% rule applies. Okay, I'll give you a few more seconds with this and then we'll move forward. Once again, the only thing we're changing here is that the Kc is now called Ka. And we make the assumption that all of these fit within our 5% rule. Okay, let's continue. You'll notice that they mentioned these boxes here. This just means concentration. You should be familiar with that. It's nothing new. When we talk about H3O plus, that's usually referring to the acid portion. Sometimes they refer to it as just H plus. So you'll see this instead. Okay. They mean essentially the same thing, hydronium and hydrogen ions. Okay. Any questions before we continue? All right. We once again make that assumption that the initial concentration should be equal to your concentration at equilibrium because the minus X or the plus X is usually insignificant. In most cases you're going to deal with here, it's usually minus X. Okay. So let's try this one out. Okay. This is a weak acid equilibrium problem. How many of you prefer that I do this one with you and you try one on your own afterwards? Okay. So I have my Ka value here. I have my concentration. When I'm writing the equation out, simply put, we're simplifying this entire thing into HPR. PR represents everything else here. So if I draw this, this is my PR. My H is still the H that it is here. Okay. So HPR will separate into H plus and PR minus. So all of that is just my PR minus, and then I get H plus. This can also be written as H3O plus. Okay. So given this information, if this is a weak acid, right away, I start with the concentration that I have, 0.1 molar, okay? This is my initial, I'm looking for the change and my equilibrium. Right away, I don't have any of this to start. There should be none of that. I know it will dissociate a little bit. You will need to balance it. The good news is this is already balanced. HA separates into H plus and A minus. So it's pretty straightforward. So you always want to make sure it's balanced, but in this one, it's usually balanced for you. So I'm always going to subtract from this side, add to this side, because I don't have anything to start with on the right side. So then this becomes 0.1 minus X. This is just X, and this is just X. Any questions up to this step here? Okay. So with that said, let me set this up in front of Ka. I'm not going to write the number of Ka for now. I'm just going to set this up. This is product over reactants, so I have these two on the top. Okay, so that's X times X. And the bottom is 0.1 minus X. Any questions about our setup here? All right. Once I do that, again, I can assume that the change is negligible. We're assuming Ka is a very, very small number. 0.1 is a large number, at least in relationship to Ka. So this is gone. So at this point, this just becomes X times X over 0.1 is equal to my Ka value. Okay, I'm going to clear my screen now. So once again, I have X squared over 0.1 equals that Ka value. Well, I'm just going to write it as 1.3 times 10 to the negative 5. The reason the X is gone, the minus X here, is because I assume that my 5% rule should fit. So if I plug it in here, right, my initial concentration, 0.1 over my Ka value, this should be a number greater than or equal to 400. Does that make sense? In fact, this is 10 to the negative 5. So we're talking about it's almost 10,000 in size. We're going to make that assumption for almost all of our weak acid equilibria. We're just going to go ahead and assume that the 5% rule works, and we can remove the minus X. Does the 5% rule matter? The minus X? If it's small enough, then it won't matter too much in terms of our overall value. But if it is large enough, larger than 5%, then it will make a difference. Does that answer your question? Okay. So we go ahead and make that assumption. I move the 0.1 over to the other side. I multiply this by 0.1, and then I do the square roots. So essentially, I'm doing this. And that will give me my value of X, which is the same as if I was just finding the concentration of H plus at equilibrium, which is also the same as finding PR minus at equilibrium. Because these two values, when I split them up into H plus and PR minus, they both started at 0. They both ended at X. Any questions so far? Okay. So just to show you the visuals from the actual details here, they went ahead and added water. I simply skipped that entire step because there's no point. Water simply has no reaction in my equilibrium expression. So H3O does because it's aqueous, and PR minus does as well. This is the same as H plus. So when I did that, I did it with H plus. Okay, so we have this all set up here. We plug it into our ice table, 0.1 minus X, everything that I did before. We assume that Ka is small, concentration is high enough that this is just equal to 0.1 without the minus X. I plug in everything here. I get to my value of X, which is my H3O plus, also known as my H plus. So it's the square root of my Ka times that initial concentration. Okay, any questions up to this part here? Okay, once we get to here, we're not done yet. Usually it asks you to find the pH. So you just need to do the negative log of this value here. Given that it's about a -3, this is anywhere between 2 to 4. So we can also check if this fits within our 5% rule. We checked in the beginning, so we knew that it did, but you can go ahead and reconfirm here. This was the concentration of H plus. This is essentially your X. So you put your X over your initial times 100, that should be less than 5%. So this is also known as percent dissociation. So how much of the H plus comes out of my weak acid? And we assume that as long as this number is smaller than 5%, then your 5% rule will work. Okay, with that said, oh, it didn't plug in the pH. Go ahead and do the negative log of this value and you get the pH value. I guess it didn't ask for that. So if you have an answer, go ahead and tell me, and we can type it on the screen here so everyone can see it. I don't have a calculator with me at the moment. Okay, 2.9 is our pH. Or 2.95, okay? Any questions about this? Okay. So Once again, I'm going to talk about percent association, which is the same thing as if I was looking at my percent error, okay? Or is how much it will dissociate, how much it will come out. So this is the H plus concentration that you are just calculated. This is the total initial amount. You times 100. This number should be less than 5%. If it is, then you're good to go in your assumptions. And another way we can look at this weak acid should produce some amount of H plus. This is essentially this one goes here and this goes here in terms of my overall equation. Any questions? Okay. So go ahead, take a minute, copy down this information. I want you to find the pH of this solution here, this weak acid, HF, given this Ka and given this concentration. All right, I'll give you about a minute or two to work on it. Okay, does anyone else still need more time with this? All right. So a couple of things we're going to do for this scenario. They always tell you to list your major species because we want to make sure we find out where the source of our H is coming from. Okay. So things that I have that produce hydrogen would be my HF, which is the weak acid, water. And if I look here, there's nothing else there. But I don't care much about the water because HF is a stronger acid compared to water. This is still considered a weak acid, but it is stronger than water. Does that make sense? Okay. So even though H2O does contribute a little bit of acid, most of the acid or the H plus is going to come from HF, and I'm going to focus on that. So that is your main source. That is your HF. I don't care about water. Okay. So let's set up our ice table. Everything else is the same. Let me see if there's a blank space. Yeah, we'll use this place. Okay. So I have HF here. HF will react with water. So if I'm doing the full thing, this is going to react water. This is liquid, so it's not going to be included in my equilibrium expression. It becomes H3O plus. So that's the acid portion. And then the H breaks off from the F here. So this becomes F minus. Okay. With that said, my concentration is 1 molar here. This, I don't care. There is no concentration and there's nothing associated with it. This is 0 and 0. So this is minus X plus X plus X. So here you should get 1 minus X. Here you should get X, and here you should get X. Any questions up to this step here? Okay. I'm going to go ahead and clear this screen. So if you need to copy anything, go ahead and copy it now. Okay, with that said, my Ka value is equal to my H times F on top, which happens to both be X. And on the bottom, it was 1 molar minus X. Now, again, good news is with our assumption rule, the concentration is 1, and then this is 10 to the negative 4. So we know it fits our assumption rule. We can go ahead and get rid of that minus X. I get rid of the minus X. I move the 1 to the other side. 1 times Ka is just Ka. So this is all gone. So all I have left is just my Ka is equal to X squared. And this becomes very easy. I do the square root of Ka, square root of this. My X, which is equal to my H plus, happens to be equal to the square root of 7.2 times 10 to the negative 4, which comes out to about 2.7 times 10 to the negative 2, give or take. Okay? All right, any questions up to this step here? All right, I'm going to go ahead and clear out the top of the screen so we can keep using this space. So we aren't done once we get to here, because once I find the value of my H plus, I still need to get the pH. So at this point, I am doing the negative log of whatever my H was, and it happens to be 2.7 times 10 to the negative 2. So this number is probably going to be somewhere anywhere between 1 and 3 in terms of pH. So go ahead and enter that into your calculator and tell me what you get. About 1.57, okay? So I'll leave that there for you. I'm going to erase the bottom of the page, and then we're going to go ahead and look for the percent dissociation. So how much of this actually dissociated out of my original amount? So here I have 2.7, right? Times 10 to the negative 2. And this is out of 1 molar concentration. Then I need to multiply this by 100. This comes out to about 2.7% dissociation. And it fits our 5% rule, and so it is justified. Any questions?
Yeah, Professor. So basically, it's to get the change in the percent. It's just basically multiplying whatever you get before putting into the log over 1 times 100, or however many moles.
Yeah, over whatever the initial concentration is.
Okay. All right.
Okay.
Thank you.
All right. Okay. Any other questions on this one? So if you found the ICE table very difficult to use in this scenario, I have an equation that will only work if, sorry, I just wrote the wrong thing. That will only work if the assumption rule already fits. Okay, so where you can remove the minus X. So if I wanted to find the value of X, which is my H plus concentration, okay, this is essentially equal to the square root of my Ka times my initial concentration, whatever that initial concentration is. I'll just write it as HA and the 0 there. So once again, this is always going to be the setup equation. My X, which is my H plus, is always going to be equal to the square root of my Ka times the initial concentration, whatever that concentration is. So in our previous example that we just did, this is 7.2 times 10 to the negative 4 times 1. And then in the earlier scenario, we had another number or another Ka times whatever that initial concentration was. And we did the square root of that. So this is just a shortcut way. If you want to set it up like this, you can always set it up. You just have to know that this only works if the assumption rule and everything else applies all the way. If it doesn't, then that equation doesn't work.
So then wait, Professor, if it doesn't work, what do you mean that it's not going to work? You mean it's not going to be a real number?
It's not going to be a minus X that you can cross out or plus X that you can cross out. Then you need to use quadratics or some other method to solve it.
Okay.
Okay.
Great, thank you.
Okay. So the next thing we're going to talk about is polyprotic acids. Polyprotic acids, the only difference here, you're still doing the same stuff that we just did before. Everything we just learned about weak acid equilibria. The only difference is I have 3 different Kas, 3 different equations. Okay. So we're just expanding on what we previously knew. Now, good news. the first Ka is going to be your largest Ka. And I'm talking about a very significant difference. So if I look here, this is 10 to the negative 3. This is 10 to the negative 8, 10 to the negative 13. So this is literally 10,000 times bigger than the next one. And this is another 10,000 times bigger than this. So this first one is essentially 10,000 times bigger in terms of the concentration compared to Ka. So Ka1 is significantly larger than Ka3. So with that information said, all of your H plus that you're going to measure is going to come from just Ka1. I don't care about the amount in either of these because they're so insignificant. The amount of change that you can get out of this is so minuscule that you don't even care about it. Okay? But you do need to know these numbers because you need to calculate the concentrations of every single thing going along the way here. Now, something I want to point out here as well. If I look at my first equation, trying to do an ice table here, we'll just make up a number. If this was 5, then this is something I don't care about. This is usually 0 and 0 to start. Okay? When I'm done with the equilibrium expression, this should be the value of x, this should be the value of x, and this should be 5 minus x. I'm making up a number here. Does that make sense so far?
Wait, can you repeat that for a second?
Sure. If I'm trying to do an ice table for just the first one, I'm not looking at anything else down here. Okay? If I
Yeah.
assume this is a 5 molar concentration, and I give you the Ka value, whatever that is, this is your Ka value. Okay? You know
Yeah.
that this is going to start off as 5. This is 0 and 0. And by the time you're done with your equilibrium expression, this is your E. It should be 5 minus x, and this is x, and this is x. Does that make sense?
Yeah. Okay, thank you.
Okay. So now that we have that, we can set up our equation. This is just essentially x squared over 5 minus x. I don't care about the minus x. I can get rid of that. And we move forward onwards and onwards. Okay. So just to clear the screen real quick, if you go ahead and do that and you solve for the concentrations of x on either of these, right? You can use this to then go ahead and find your pH like you normally would. But we need to go ahead and factor this in as well. If I solve for this concentration at equilibrium, this is H2PO4. Okay? This has a particular concentration. It's the same as this X right here. So whatever this X here is the same thing here. I can go ahead and just apply it for this one right here. So my starting concentration for this is just the previous X. Okay? Again, I don't care about water. These are new terms, so I'm going to just call these Y. So to find my value of Y, this is it's eventually going to be X minus Y. Okay? And these start off at 0, and then this eventually becomes the letter Y. I'm using new letters here, so just so you don't get confused. Okay? When I get to here, this Y, if I look at this value of Y, it is so tiny compared to the value of X that I can almost throw it out. All right, just want to clarify that. This X right here is the same as this X right here. This new value of Y goes right here as well. So we can continue doing the same situation. I'll use the letter Z, okay? 0 and 0, Y minus Z, and then here it is just Z and Z. Again, the values of Z here and Y are so insignificant that we can toss it out. But if they want you to find concentrations of these values, you need to include those numbers or those letters. Does that make sense so far? So you're doing ice table, but it's a series of ice tables. So this is X minus Y for this part right here. This is X itself. Yes, Y is also equal to Y here. Yes, we also can ignore the assumption for Y and Z as well. So that is correct. So when we get to here, this is essentially ignored as well. And same thing here. Does that answer your question? Okay, I'll take your silence as a yes then. All right, so let's go ahead and give this a try. We can look at some polyproduct examples here. They are either diproduct, so 2 of them, or triproduct, 3 of them. Okay, I haven't seen any one with 4 of them because it doesn't really exist. Usually it's 3 or 2. Okay, with that said, let's go ahead and try this problem together. Okay. We are looking for the pH. You're given this concentration right here. It's H2, so this is diproduct. You're going to run into two of these equations, okay? It also wants you to find the equilibrium concentration of these three things. So H2 ASC, HASC minus, ASC2 minus. And they also give you Ka1 and Ka2. Now again, ascorbic acid is this long thing right here. We are simply just saying that we have H2 and we're putting the rest of this as ASC to simplify it, okay? So the first thing you want to do here is set up the initial equation. This is the one with Ka1. So I have H2, and then I'm just going to write ASC for the short. I'm not going to write this whole thing out. This will break up into H3O plus, like we usually have, right? And then ASC, HASC minus, okay? We're only dealing with the first hydrogen here. So given this setup, what is my concentration of H2ASC? Not a trick question here. Okay.
0.050.
0.05 M. These are zeros, okay? I have the normal setup, minus X plus X plus X. This becomes X. This becomes 0.05 minus X, okay? Now I'm going to plug everything in. My Ka1, I know that value already, but I'm not going to write it yet, okay? This is the same as if I wrote X squared over 0.05 minus X. And again, with the assumption rule, I can go ahead and remove that. So you go ahead and move it over to the other side. You have Ka1 times 0.05. You do the square root of this and you get your value of X. Does that make sense?
Oh wait, so just Professor, just out of curiosity. So whenever it has H26H H26CH6O6, that means that it's H2 plus whatever is becoming H3O and then the rest of it, correct?
Yes, so essentially what's happening here, if I look here, it's the same as if I just wrote in water, right? Liquid. And remember, this doesn't get included in my equilibrium expression. I just completely left it off. This one H goes here. Then whatever's left over is that. Does that make sense?
Yeah. Okay, I just wanted to confirm that. All right, thank you.
Okay. So once we get to here, we have found our value of H plus, okay? Also known as H3O plus, if you want to just write it that way. Whichever one you prefer. They mean the same thing. But I also found the concentration of this one, HASC minus. So technically I have this value already. It's solved, it's done. I can find the pH now by doing the negative log of this value here. And I have just solved for that as well. And this is all with a standard ICE table. I haven't done anything different, okay? So I'm gonna go ahead and clear the screen real quick. To do the next one, Ka2. Remember, at this point, you have already lost one hydrogen. So this is HASC minus, that's what you're starting with. This is going to go ahead and lose the other hydrogen. So it becomes H3O plus, and then it becomes ASC2 minus. So this has a concentration, whatever that value is of X from before. Okay, I haven't changed that value. These both start at 0. Actually, this technically doesn't start at 0. This one starts at the value of X. Okay, now I'm going to obviously subtract from the left side, add to the right side, because this is 0 on the right. So I'm going to use a new letter here. Once again, minus Y, plus Y, and then plus Y, okay? By the time I'm done, this is just X minus Y, X plus Y, and then this is just Y. So what rule can I assume again?
That Y is insignificant. We can use the assumption rule.
The change in the Y is insignificant. So I can go ahead and cross that out. I can go ahead and cross that out. Okay. The only one that does matter is just Y by itself. The change in Y compared to whatever the value of X here was is insignificant. So let's set this up. This is the next one here. Once again, I have Ka2 is equal to, this is now X times Y over X. So what do you notice about this? What can I cancel out?
The X.
The two X's can disappear. So it just so happens that my concentration of Y here is equal to my Ka2 directly. So I don't need to do anything else with that. So I have essentially found this, 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 and this. Does that make sense? Take your silence as a yes. Okay. So just to show you the visuals of what they do, they set up both Ka1 and Ka2. These are how you dissociate each of these hydrogens, okay? We're gonna focus on that first equation right here. 0.05 minus x, we get rid of the minus x over here. You do the square root, you find out the concentration of this first one is 7.1 times 10 to the negative 4. That is equal to this and equal to this. And then you do the pH of that, you get this value right here. Okay, so you have the pH again, you have this concentration, you're good to go. The only thing you're missing is the original one and then the next one afterwards. The original one, once you find the value of x, which is this, you can plug it back into this equation and actually solve for this. So this essentially, your concentration for this is just 0.050 minus 7.1 times 10 to the negative 4. Okay, once we do that, you can plug that in, just as I mentioned right here. You get that value, you have this, and you have, well, the next one is what we're going to go ahead and solve, this one right here. Here we said the same thing. Remember what we said, this concentration right here is just this value. So this is just the same thing between these two. And we know what this was, okay? This was just simply your value of x, this is your value of x. They cancel each other out. To solve for this, it is just equal to Ka2. Any questions on this? Okay. With that said, I want you to try this one out on your own. This involves 3 of our Kas, 3 of our equations. Once you are done solving the ice table on the first one, everything else just becomes algebra. So go ahead and give this a try. Okay, does anyone else still need more time with this one?
Professor, I got KA1 and KA2, but how do we solve for KA3 again?
Algebraically, you should be able to solve all the stuff. Ka3 itself is given to you, but the concentration wise to find PO4 3 minus is just algebraically.
Okay, thank
Okay.
you.
All right. I'll give you a little bit longer to work on this and then we'll go over it. Just a quick check. Are either of the co-hosts recording the meeting? Okay. Okay, so let's get started with this question. It's going to take a little bit of work, so let's go ahead and set it up. Let's take a look at Ka1 first, okay? I'm not going to rewrite the Ka1 value, but I'm just going to simply look at the first equation. I'll try my best, but sometimes I forget to upload it or it may not upload directly right away, so it takes extra time to process it. So if you send me a reminder from the weekend, I might be able to upload it or before that, okay? All right, so for the first one here, I have H3PO4, and that is going to eventually change into H2PO4, PO4 minus, and then it's also going to change into H3O plus. Or I guess in this case, we could just write it as H plus, okay, to make it easier. Now, I'm also going to set up Ka2, so you can see the general equations here. H2PO4 minus, that's where we start. And this is going to change into HPO4 2 minus plus H plus again, okay? And then our Ka3 is going to be HPO4 2 minus, and that changes into PO4 3 minus plus H plus. Any questions about this? Okay, so I'll leave this here for now. We will revisit some of these. So let's start with our very first one, okay? I have H3PO4, and then I know that I am changing it into H2PO4, and then H plus. Okay, this starts with 0 and 0. My initial concentration was 5 molar. Since this side is 0, I do minus x, minus x, minus, oh, sorry, plus x, plus x. Okay, so this on the left side becomes 5 minus x. Let me go ahead and just drag this out of the way. X and x. Any questions on that so far? Okay, With that said, I can rewrite this as Ka1 is equal to x squared over 5 minus x. And again, I can go ahead and ignore the minus x under the 5% rule, and we can go ahead and move forward from there. This just simply becomes square root. So x is equal to the square root of your 5 times your Ka. Anyone have questions up to this step right here? All we did right now up to this part was just weak acid equilibria, as if we were solving for the H plus value of a weak acid. Okay, assuming no one has trouble getting up to here. I'm going to go ahead and clear the screen now, or most of the screen. Okay, so let's go ahead and focus on the next part. So the next part is I'm going to look at just Ka2. So for Ka2, I am starting with H2PO4 minus, and this changes into HPO4 2 minus and H plus. Okay. In the previous thing, I want you to go ahead and calculate what our value of X was. So whatever our H plus value was, also known as our H2PO4 value. Anybody have that number? It is not 0.0375. It is 0.19. Okay, so this is the concentration of your X. So when I go ahead and get started with this next part here, we're going to reuse the letter X, okay, just so we don't get confused with more stuff. The initial concentration here for our second ice table, if I were to set this up, is 0.19, 0.19 here, and this is 0, okay? So if I'm reusing the letter X, this is minus X here, plus X plus X. So this becomes 0.19 minus X. This is just X, and this is 0.19 plus X. Okay, is everyone following along so far? So I'm going to put something to the side here on the very top left corner. I know that my H2PO4 minus concentration is going to be equal to 0.19. Okay, so I got that from this part right here. I also know that my H plus concentration is equal to 0.19. So these are all things that I figured out. I'm going to go ahead and just clear this part right here. I don't need that information anymore. I'm going to rewrite this in terms of our Ka. So here I have my Ka2 is equal to X on top from this HPO4 2 minus. Here I have 0.19 plus X. And then here I have 0.19 minus X. So what can I assume again? What assumption can I make again?
You can cancel out the 0.19 plus X and the 0.19 minus X.
So not the entire thing, but I can cross out this and this first, okay? And it just so happens these two are the same number, then I can cross them out. Does that make sense? Sometimes the numbers are different, then you can't cross them out. But for the purpose of today, it happens to be the same number. So when I am solving for this value right here, I can now write down that my HPO4 2 minus is equal to my Ka2 value. So whatever this is. Okay, I'm not going to write the number in, just saving myself some steps. Any questions up to this part? Okay. So I'm going to go ahead and erase this and then clear out the ice table that I have on the bottom here. Okay, let's do one last one. Let's go ahead and take a look at my Ka3. So here I have HPO4 2 minus, and that changes into H plus and PO4 3 minus. Okay, setting this up here, I know my value here is just the value of Ka2, whatever that is. My H plus is still 0.19. I haven't changed that value. My PO4 is 0 to start. Okay. And I always minus from this side, add to this side because this is 0. So this becomes Ka2 minus x. This is just 0.19 plus x. And then this is just x. So when I set up my equation here, I'm looking for Ka3, right? So I have Ka3. I know this is related to, I just drew an extra line there. So it is related to your x from your PO4 3 minus 0.19 plus x, and then Ka2 minus x on the bottom. What can I cross out here?
You can just cross out the plus x minus x. And
And
no,
cross
you
this
can,
out and this
Oh.
out, okay? Because we again assume that it's insignificant. Now remember, I mentioned that we can't just cross out the entire thing because this 0.19 is now different from this value right here. Okay, so now I know this value, I know this value, I don't know this one. This is my only one I'm missing. I can algebraically solve for this. So move everything away from it, solve for x. That is how you get the concentration of this one right here. Okay, so if I wanted to write that down, this is essentially the same if I took Ka3 times Ka2 divided by 0.19. If I want to algebraically write it, because I'm too lazy to solve it for it right now. Okay. So let me clear all this out. Once this is out of the way, are we finished?
yes.
No, right?
No, we have to find the pH.
We have to find the pH. Okay. And this pH is just simply the negative log of 0.19, because that was my H plus concentration. Does that make sense? That comes out to about 0.72. Are we done now? So we have one more thing we have to find, the initial concentration, the concentration of H3 of PO4, the original. So remember, this was equal to at equilibrium 5 minus x. Previously, we just got rid of the minus x. So we said it was such an insignificant change, we don't care. But I actually have the value of x now. This is my value of x. So this is 5 minus 0.19. That's going to go ahead and give me my 4.81. Okay. So now I have found all 5 pieces that it asked for. So if you look carefully here, it says find those 5 pieces and you go ahead and answer that question. Does this make sense so far?
Yes.
Okay. Now, I know we went through 3 different ICE tables. Is it okay if I clear the screen? I'm going to go ahead and clear the screen. If you need more time to copy, let me know. Okay. So even though we did 3 different ICE tables, I only needed 1 ICE table. And the reason why is because I always assume that my secondary concentration, or technically tertiary concentration, is equal to my Ka here. Algebraically, I can cancel things out. Okay, because this is my x right here, and then H plus is my x. So the 2 of these are usually canceled out, and I'm left with just this, which is directly equal to my Ka. Okay, so algebraically, I can solve that. If I wanted to set this, my last one up, I can say my Ka3 is equal to, and then we just simply draw the pieces that we have here. Okay, I have H2, HPO4 2 minus, so that's where I started, right? Oh, sorry, that should go down here. HPO4 2 minus, and this is essentially just my Ka2. So I don't have to change that value. I just write Ka2 here. And I know up here it's H plus, which I already know the value is just my X, the 0.19. Okay. And then I also know that the last thing I need to find is PO4 3 minus. So at this point, it's all just algebra. I'm just trying to find PO4 3 minus based on the information that I have here, moving things around. Any questions? Okay. So question for you, how likely are you to see a polyprotic acid question in your quiz? That's correct, very likely, okay? So make sure you understand how to do this. So next thing I'm going to talk about is a weak base equilibria. Very similar to the weak acid. Instead of your HA, so your acid, right, joining with H2O and then making
Wait,
H3O plus and A minus, we're doing the opposite.
Professor,
Yes.
for that question that you just said, it's very likely we would have it. It would be for chapter 18, right?
Yes.
Okay, thank you.
Okay. So in this scenario here, again, the acid was, I take the H and I join it with the H2O plus, so I make this and I get this left over. The base, opposite the other way. I take the H from the water and I make OH. In these scenarios, you do want to write down the water because you need to find a source of that H. That H comes from the water and you have this left over. We are essentially finding this value. This is my X. Okay. And this will tell me the concentration of OH minus at equilibrium. Any questions? Okay. So with that said, an example of here, I have an amine. It joins with water. It takes in that H. It has OH minus left over. We are essentially measuring this OH minus. Just some examples of base values. We don't really need to memorize this. This is already here. Let's go ahead and give this a try. Same setup, same format, except that you are dealing with OH instead of H for bases. So I'll give you some time to work on this and then we'll go over it. Okay, does anyone else still need more time with this one? All right, so let's get started then. So we're just gonna go through this as quick as possible. Same setup, but this time I'm looking at Ka. Instead of Ka, I'm looking at Kb. The setup is almost the same. It joins with water, but in this case, I'm making OH instead of H3O plus, and then the H goes from here to the base itself, okay? So with that said, let's plug it into our ice table. I start with 1.5, 0 and 0 on the other side. I get 1.5 minus X, X and X on the other side. We assume the same situation, that the minus X is negligible, okay? Based on the value of Kb and the value of my initial concentration, which is 1.5. So I plug it into my Kb expression the same way. I'm here to solve for OH minus instead, which happens to be X here, and this is also X. So it just becomes X squared over 1.5 is equal to my Kb value. I reconvert everything into OH. Once you get to here, up to this step is almost the exact same you would for weak acid equilibrium. The only difference here is now I need to change this into either H plus or directly into pH. So it's an additional step. Does anybody remember how we change OH minus to H plus? Or if you want to change this directly to POH, you can do that as well. And then both of these lead to here.
Do you divide by 1.0 times 10 to the negative 14?
So 1.0 times 10 to negative 14 divided by this. So your 10 to negative 14 is divided by whatever that number is. And then that will give you your H plus concentration, which then you can do the negative log to find the pH. Okay, if you start with the negative log here, it works as well. You can find the POH, then you do 14 minus your POH, and that'll give you your pH, whichever one you prefer to work with. Any questions? Okay, we can also check the assumption rule. If it, in other words, our dissociation, if it fits, then we're good to go. And this one fits, it's about 2%, so it's less than what, less than the 5% rule, okay? And then finally here, they went ahead and solved for the pH. If you are dealing with a weak acid, your pH should be less than 7. If you're dealing with a weak base, your pH should be greater than 7. If you are not getting that number greater than 7, you did something wrong. Any questions up to this part? I always strongly recommend justifying it, whether in the beginning with the initial concentration over Kc or initial concentration over Ka, and count that as greater than 400, that can justify it, or at the end when you go ahead and find the change, do the change over the initial, and if that's greater than 5%. Yeah, you always want to define, you always want to make sure that's justified, because if it's not, then you have to use quadratics or some other method. Okay. So let's talk a little bit about the acid strength, and we're going to focus on the non-metal hydrides. Okay. So if we go across a period is diagonal here. Oh, sorry, not diagonal, it's horizontal. So you go from left to right across the period, the acidity increases, so the acid strength increases. Okay. And the reason why this is the case is because electronegativity increases across a period. Now, if we go down a group, and the reason why we go down a group and the acid strength increases, we get larger and larger shells. This goes back to Chem 1. The more shells you have, the further out the electron is, the further out the hydrogen is in terms of bonding. So there's less bond strength. So it will not hold it as tightly, okay? That means it's easily letting go of a hydrogen. And what is the goal of a strong acid? Well, what does a strong acid do? How do I know something is a strong acid versus a weak acid? It dissociates. Remember, dissociate means how easy it is to break apart, to separate, okay? So the stronger the acid, the easier it is to take the H away. It's easier it is to give away that H. That's what it means to be a strong acid. Okay, so to give you an example here, electronegativity increases going to the right. That means the acidity increases going downwards. The acidity increases as well. So we know that this is a weak acid because they are very, very close together. The spaces are very small, so it has a stronger grip on that hydrogen. The fluorine will not really let go of this hydrogen. So that means that this is going to stay mostly closer to the fluorine. That means it's a weak acid. Everything else here is considered a strong acid. And as we go further down, these are stronger acids compared to the previous one, based on the information that we've written. Okay. So the next thing we're going to talk about is the strength of oxoacids. So remember we said oxoacids are where we go ahead and look at the number of oxygens versus the number of protons. Okay. If there are 2 or more number of oxygens compared to number of protons, then it is considered a strong acid. Another way we can define this is if it is essentially the same thing, but there's more oxygens attached to it, the stronger that acid is. Once again, the more oxygens that we have, the stronger the acid. So if I wrote something on the board here for you, which of these two is a stronger acid?
The second one?
The second one, the one on the right side, okay? So both of these are considered strong acids, right? Because this has 1 proton and it's 2 or more number of oxygens. Okay. So this one, they fit in the strong acid category, but this one is stronger because it has more oxygens. Okay. So again, this is just relative strength that you can see. The more oxygens that we have, the more easy it is for that hydrogen to dissociate and separate. So the stronger the acid. Okay. Now we're going to learn a little bit about salt yields. This is a very, very difficult topic for most people to handle. For some reason, they just don't understand it. And there is an ALEKS associated with it that a lot of students have issues with. Okay. So the first one I'm going to look at are neutral salts or neutral solutions. So I want you to pay attention. It says cation of a strong base, anion of a strong acid. So what I mean by that, if I take a look at NaOH and then I look at HCl, these are both strong acids, strong bases. Okay. This is my strong base. This is my strong acid. When I refer to the cation, I'm referring to this positive charge right here. I don't care about the OH. The OH itself is my base. That makes sense? I don't care about it. It doesn't exist. All I have is Na+. When I talk about the anion of a strong acid, I'm referring to this part right here, this chlorine. Okay? I don't care about the H, and there is no H present. So in this solution, I only have Na+, which is a cation of a strong base, Cl-, anion of a strong acid. So really quickly, what is the goal of a strong acid or a strong base? What do they want to do? I know someone answered already, but we're going to keep emphasizing this point so you get it.
Dissociate.
Dissociate, right? They like to separate. So if I took HCl and I separated it, now I have some H and I have some Cl-. Does this Cl- want to rejoin with this H?
No.
No, right? It wants to stay separated. Think of this as a divorce. It does not want to get back with that person at all. Okay? So remain separated, is happy being separated. Because strong acids tend to separate, right? Their strength is how well they separate. If they separate really well, then they don't want to rejoin really well because that defeats the purpose. Okay. So this will separate. This remains happy separated. Okay. It's happy being single. It doesn't want to join back with an H. This is also coming from the same situation. Happy being single does not want to join back with OH or anything else. So these two are both sitting in water. In water, I have two things. I have hydrogens and I have hydroxides, right? Because water is made up of your hydrogen plus your hydroxide. This does not want the OH. This does not want the H. They both are content being separated. They do not want anything to do with water. They just sit there. Okay? So while there is some interaction in terms of intermolecular forces, we don't really have to worry about that right now. In terms of overall attraction, no connection whatsoever for bonding. So they just sit in water. They don't do anything. Both of these are essentially, you could just say they're docile. They don't really move. Okay. So they won't change the water into being OH or H+. So that is why this makes this neutral. Does this make sense so far? Take your silence as a yes. Another example we have here is NaNO3. NO3 comes from HNO3. Again, I don't have this H present and I don't have this OH present. It is not in my solution. I only have the Na and I only have the NO3. It's just named this way because you know this is the anion from a strong acid, cation from a strong base. So once again, neither the Na+ or the NO3 will react with water to any greater extent. Okay, any questions up to this part? All right. Next scenario, I'm going to look at an acidic solution. So these two salts combined will make an acidic solution. So if we look carefully, again, I have the term cation and I have the term anion, right? The anion is still going to be associated with my acid. The cation is still going to be associated with my base, okay? Anion here, I can go ahead and use the same anion here. I have Cl-. This is not going to interact with anything. Can we agree on that? It's happy being separated, remains separated, doesn't want to deal with anything. If I look at a weak base, NH3, what do weak bases and weak acids tend to do? Nope, they don't tend to dissociate. That's a strong acid and strong base. They tend to remain together, okay? They do not like to separate, they remain as one. If for whatever reason I change NH3, it is no longer NH3. It wants to remain as NH3. I do something to it where I make it into NH4. So I give it one more hydrogen, okay? So this is the cation of a weak base. So this has an extra H plus. What does this want to return to being? What is it most comfortable with? It's most comfortable being that base, right? It wants to return to being NH3. Does that make sense? It started off as NH3. It doesn't really want to add or remove hydrogens. Somehow a hydrogen was given to it, okay? Now it's an NH4. It doesn't want that hydrogen. It wants to return to being NH3. So in the process, that H plus is going to leave. It's going to forcefully get rid of that H plus. I don't want it. It's going to say, I don't want it. Please take it away. If I put this into a solution of water, the Cl minus is not going to take it. It doesn't want it. Who's going to end up taking that H plus? I have a random H plus floating around. Who's going to end up taking that H plus?
Ammonia?
The water is going to end up taking it. Okay? The water can act as an acid and a base. So when this takes it, it becomes H3O plus. So now in my solution, I have NH3, H3O plus, and Cl minus. My H3O plus makes the solution slightly acidic. So this solution is slightly acidic because of this cation from the weak base. Now, once again, it's nothing to do with our strong acid. The strong acid did not make this acidic. It is the cation from a weak base that wants to return to being in NH3, a weak base, and wants to get rid of the extra stuff that it was given. This extra stuff will essentially make the water more acidic. Does that make sense? I'll take your silence as a yes then. Okay. Another scenario, more acidic solutions, same situation. This time, again, anion of a strong acid. This is not doing anything. It's not affecting our acidity here because it's happy being separated. It doesn't want to join with anything. But a highly charged metal cation, which we're going to learn about later on, it will try to interact with things. So it will go ahead and try to join with water. In the process, it will make the water acidic. Any questions so far? Okay. Other scenario we're going to take a look at. Basic solutions. So here, if you notice the naming, we no longer have anion of a strong acid. We are now looking at the anion of a weak acid and the cation of a strong base. So if I use Na, for example, Na plus, this has nothing, sorry, with the Na plus, this has nothing to do with our water. It will not affect the water. It will not interact with anything. It will just stay put on its own. What does affect it is my weak acid. If I look at a thing such as HF, this is my weak acid. If I were to dissociate this and remove this, it just becomes F minus. What does F minus want to do? Or what does it prefer to do? Neither of those things. It wants to rejoin with the H to make HF. It wants to remain as a weak acid. It doesn't want to separate. Okay, think of this as a clinging significant other. They will not let you go. Okay, they want to return to being together. So this is always going to try to reform HF. So in the process of reforming HF, this is what I have in the solution right now. H2O, F minus, and Na plus. Where is it going to get the H from to become HF? Where does it pick up that hydrogen? From the water, right? When it picks up from the water, then what happens to our water? It changes into OH minus. So what I have in my solution now is this: Na plus, HF, and OH minus. So OH minus makes my solution slightly basic. Does this make sense to everyone so far? So remember, the thing that is actually contributing to if something is basic or acidic is not going to be the component from the strong base. It's actually going to be the component from the weak acid or weak base. Because the goal to return to being a weak acid and weak base makes it react with water as a response. Okay, let's continue. The last one we're going to take a look at is going to be a scenario where we are dealing with the anion of a weak acid and the cation of a weak base. Well, actually, we'll deal with that in a second. I want you to go ahead and try to tell me if this is acidic, basic, or neutral based on the information that you see here. So just looking at the left side and the right side, cation and anion, tell me if you can figure it out. Okay, let's get started with this then. If I look at the first one here, I have KClO4. Now I know my cation comes from some kind of base, and then my anion comes from some kind of acid. Okay, I can go ahead and just put an H here. I can just go ahead and put an OH here, and we can technically see what we're looking at here. So HClO4, this is considered a strong acid. KOH is considered a strong base. But remember, we don't have either of these. We have just their components next to it. So this is easily dissociated. This is also easily dissociated. So they like to separate when you place them in water, and they like to remain separated. They do not want to interact with anything. So, but both of these want to sit in water, and they will not interact with water. They will have no desire to reattain the OH or the H+. So this makes this a neutral solution. Okay, next one. Here I have Na on the right side. Then I have the benzene or benzoate right here, okay? So I put that to that side. It's essentially missing a letter here. This is Na plus, COO minus. So where is this one from and where is this one from? Remember, your Na is your cation. So it should always be joined with what? In most cases,
Base.
with my base OH. And this involves C6H5COOH, okay? That's essentially my carboxylic acid. This is a form of acid. Now, if I look here, this is coming from a strong base, right? Will this interact with anything? Strong bases tend to separate. No, right? So this is not going to interact with anything. This is not one of my strong acids, so this is actually considered my weak acid. It doesn't have its H. What does it want to do? It wants to obtain another H, okay, to return to being a weak acid. It needs to find a source of H. The only source of H here would be from water. So it takes away one of the H's. What you have left over is some OH minus, which essentially means that the solution is basic. So once again, because of the anion of the weak acid, it will cause the solution to be basic. This is why a lot of people get confused. Okay, last scenario. Is this going to be acidic, basic, or neutral based on the information that you see? Someone unmuted and tried to say something, didn't hear anything.
Acidic.
It is going to be acidic, that's correct. The reason why it's going to be acidic is not because of the strong acid anion, but because of the highly charged metal ion or metal atom. Okay, so we'll go through each one of these. Since we covered everything, it's already pretty straightforward. That's what it is for the first one. It'll be neutral. Second one, it will be basic because the weak acid wants to return to being a full weak acid. And then the third one here, small metal cation. That's what's going to essentially cause this to be acidic. Okay. Last thing we're going to talk about is a scenario where we have a weak acid and a weak base. Okay. The cation and anion of a weak acid and a weak base. Before we jump into this, actually, I do want to bring up one other thing. If I look at a solution here, NaF, okay? You know, this comes from a strong base. It doesn't make a difference. The F, what is F in comparison to HF? What is it called? What's another term for it? Starts with the C. They have a difference of 1 proton. Not cation. The difference is 1 proton between these two things. And that also means that their Ka times Kb can be multiplied, and that will give you Kw, only in this specific scenario. Okay, I guess nobody knows it. You have conjugates here, okay? HF, oh, F minus is the conjugate base of HF. Does that sound familiar? Does anybody remember that? No, you don't remember conjugates? Okay, I recommend looking back at the beginning of chapter 18. We covered that. So the difference between your conjugates here is a difference of 1 hydrogen. I take out the hydrogen, this is the conjugate base to this weak acid. Okay, if I flip the scenario and this was my base, this is the conjugate acid to that base. They add 1 more H. Okay, so with that said, remember, HF and F minus here, this is a weak acid. This is still considered a weak base, but in terms of strength, this base is stronger than water. So if I put F minus and water together, this will function as the base. This will function as the acid. It will take away an H in the process. If I put Cl minus into water, even though this is taking a base, this is a very, very weak base, weaker than water. So that water is a stronger base than chlorine. It will hold on to its H more so than chlorine will be willing to take it. Okay, any questions? All right. So with that said, when we go ahead and look at situations where we have cations of a weak base and an anion of a weak acid, I need to go ahead and figure out the relative acid strength or base strength of the ions. So NH4 is essentially the conjugate acid to this weak base. Cn minus is the conjugate base to this weak acid. Okay. Now I don't have the actual weak base or the actual weak acid present. I do have their conjugates present. So this is the conjugate acid, this is the conjugate base. I need to find out whether this conjugate acid is stronger than this conjugate base or the other way around. Because the middle piece is water. So they have water in the middle. The stronger one is going to influence the water in a greater amount, and that's going to determine if this is acidic or basic. Okay, so with that said, let's go ahead and look at the values of our Kas and Kbs for each of our weak acids and weak bases. So here's where we're set up here, okay? So first, we know our Kb of NH3 and we know the Ka of HCN. We don't know these two things here on the left because these are not things you normally try to remember. So you know these, they usually tell you these things and list it, okay? Now to find the Ka of this one, given the Kb, you know that is related to Kw because these are conjugates. So Kw divided by Kb will give me Ka. And then the opposite is true. The Kb value here gives me that one right there. So remember our scenario, what I told you, the strength of the acid, as that increases, the strength of the conjugate base goes down. So if I decrease in the strength of the acid, the strength of my conjugate base goes up. This applies in this scenario as well. So looking at this, this is my base and this is my acid. Looking at these two numbers, which one is stronger? Or which one has a higher value? The base has a higher value. It's 10 to the negative 5, right? That's way more higher than 10 to the negative 10. So they're conjugates. This is conjugate acid, and this is conjugate base. Should be the opposite. So my conjugate base of this weak acid should be stronger than the conjugate acid of this weak base, because the conjugate is usually the opposite. The stronger the acid it is, the weaker its conjugate base. So this is essentially my conjugate base, and this is essentially my conjugate acid. Which one of these will contribute or interact with water more versus the other one? The conjugate base. So this is a higher concentration, right? A higher value of Kb. So it's going to go ahead and take away that H. Okay. This is going to give away its H. This is going to take away the H. So it's going to happen and it keeps exchanging. But at one point, NH4 is going to give away enough and say, okay, I'm good. But Cn minus is going to keep taking. So it's going to keep taking from the water. We have a lot of water present. Okay. So every time it takes it away, we make OH minus. Every time this gives it, it makes H3O plus. And then these two cancel each other out. But at one point, this is going to stop. It is no longer going to give away H plus. It's done giving away H plus. But this is going to continue making more OH minus. So my solution in this scenario is basic because this conjugate base is stronger than this conjugate acid. And that's because the opposite is true here. The base is stronger than the weak acid, or the weak base is stronger than the weak acid. Any questions? Okay. So let's continue. We don't need any of this other stuff. It's pretty straightforward. You can see some of the general results in terms of their behaviors. There is going to be a question on Alex that may be a little challenging. You need to be able to understand whether or not it is the cation or anion of either a strong acid, strong base, weak acid, weak base, whatever it is, that affects it. It's always the weak ones that affect it, not the strong ones. The goal of the weak one is to return to being the original weak value. So the original weak base or the original weak acid. And it will use water to help itself do that. Okay. So let's move on to the last definition that we have. This is a Lewis acid-base definition. The main difference here is that Lewis said, let's not look at protons. Let's look at electrons. So he kind of flipped the scenario. He simply said that a Lewis acid, instead of donating protons, it is now an electron pair acceptor. It accepts electron pairs. And then a Lewis base, it's the one that donates the electron pairs. So we're looking at the movement of electrons now. So the good news about this is that Lewis didn't really expand on the definition of a base. This is pretty much the same exact thing. He just changed the naming to electrons, okay? The base is already defined here. We know that it is the one that accepts protons. In order to accept a proton, you need to have a negative charge. To pick up a positive, you need to have a negative charge so that they can cancel each other out, okay? Lewis acid, however, did expand on a lot of definitions. Anything that essentially can accept electron pairs and accept a negative is considered an acid now. It doesn't have to have H plus. It doesn't need to have a proton. So no H is necessary. Okay. So with that said, some examples here. well, I guess we're revisiting this just so to clarify it. Lone pair of electrons to donate, that's for your base. The acid must have a vacant orbital. In other words, it can go ahead and receive those lone pairs. Okay. Once again, it expands on the definition of acids. So with that expansion, we actually now can look at elements that have nothing to do with H. So we don't need H anymore. We don't need protons. If I look at an example here, aluminum and boron, these are your electron deficient molecules. These are your exceptions when we're talking about the octet rule, back when you learned about the octet rule. Okay. They can actually, they are electron deficient. That means they can go ahead and accept more electrons. That means these can function as acids. So aluminum and boron can function as an acid. And this also means all the highly charged metal atoms can also function as acids. So when we learned about our salt yields, the highly charged metal atoms essentially are your acids. Okay, any questions? All right. You don't need to know too much about this, but this is just where there are multiple polar bonds. I won't go into too much detail about this. Just know what we mentioned about the Lewis acid definition. If you plan on taking organic chemistry, this is a good slide to review and everything else with Lewis acids and bases in general. So they will touch upon this stuff later on. But for the purpose of this class, all you have to know is the main definition and what kind of acids are now included for Lewis acids. Okay, metal cations, same thing. These can now function as acids or Lewis acids because they can receive a lone pair of electrons. So they can accept lone pairs of electrons. And you form things such as ligands, which again, I won't go into too much detail about, but if you take advanced inorganic here, they will talk about ligands in detail. So this is all about advanced inorganic. What you're taking right now is considered regular inorganic. Or they just call it general chemistry. Yes, I am. Okay, some ending reminders for this chapter, okay? You should know your 3 different acid-base models and how they have progressed. So how they built off of one another. You should memorize those strong acids and strong bases list, and everything else is considered a weak acid or a weak base. You know that a small Ka usually means you can neglect the positive or negative minus X or positive plus X. Same thing with a small Kb. So we'll always try to go with our assumption rule, the 5% rule for the time being. If you have any of these values, pH, POH, H3O plus, or OH minus, you can find the other 3 algebraically. Anyone have any questions up to this part? Okay. Does anyone else still need time to copy this down? All right. For the meantime, those who are co-hosts, go ahead and I'm going to go ahead and ask you to stop recording. I'm going to go ahead and remove the co-host permission in a second. Okay, so we're going to go ahead and begin the poll. You should be able to see the poll now. There's only 3 questions. The first one is a single choice. Second one is multiple choices. Third one is also a single choice. Okay. So I'll give you about 2 minutes to work on this, and then we'll finish up the slide here, and then we'll call it a day. Okay, you have about 2 more minutes. You have about 1 more minute. You have about 30 more seconds. Okay, please finish up whatever you need to do. I'm going to give you about 10 more seconds and I'm closing the poll. Okay, so let's take a look at the results. Do you need an ice table for strong acids and strong bases? The answer is no. The reason why you don't need it is because you already have the H plus concentration or the OH minus concentration. You just use that to find your pH or POH. So you have no need for the ice table, only for weak acids and weak bases because some of it dissociates. So what determines the strength of a salt? The main determination is going to be the anion of a weak acid or the cation of a weak base. The anion of a strong acid and the cation of a strong base do not contribute to that. They essentially don't affect it at all. The last one, Lewis acid base model, which one of the following makes which one of the following an acid? And the answer is actually going to be, aluminum. Only 5 students put that down. Okay. The Lewis acid base model tells us that aluminum is now an acid. Everything else that was there, water, H3O plus, HNO3 is already an acid. HF is already an acid. NaOH is not an acid at all. Okay, with that said, let's go ahead and finish up the last bit of the ending reminders. Why do chemistry instructors like to teach about ammonia? Because it's basic material. Okay, next week we will start chapter 19. If you're going to attend office hours, give me about like 5 minutes and I'll start setting it up. If you have any other questions, you can send me by an email or you can come to office hours. All right, other than that, we are done for today and I'll see you all next week.
Have a great week, Professor.
You too.
Bye.
Professor, before the thing ends, for the poll that was put at the end, I put an answer for each and every single one, but it says I didn't answer it on my end. when I physically clicked each one.
Did you click submit already?
Yeah, I had clicked submit and then it was
Okay, I'll
like,
take a look on my end, right?
yeah,
I can also see that you wrote that in chat, so it'll save that in chat for me. So then just in case I can refer back to that.
okay.
Okay.
Alright,
If it's
thank you.
not there, if you missed one poll, it's okay.
Well, yeah, but I'm just saying because for some reason it said I didn't answer it, but I clicked. I actually remember which ones I clicked. So
Yeah, don't stress about it. If you missed one poll, you missed one poll. It's okay.
okay, all right.
Okay.
Thank you so much, Professor.
All right. Enjoy
All
your
right,
day.
have a good